Hi everyone, I am Sam. Today we are going to talk about physics. Physics is the study of the fundamental forces of nature and the properties of matter and energy. It explores everything from the smallest particles of matter to the vast expanses of the universe, trying to answer the big questions. Why does the apple fall from the tree? How does light travel through space? What makes atoms hold together? Physics helps us understand how the world works, whether it's the motion of a car on a highway, the behavior of light through a magnifying glass, or the forces that shape the stars. To begin understanding physics, we must first grasp its foundational concept: forces. A force is simply a push or a pull. It can change an object's speed or direction, or even cause it to change shape. Gravity is a force that pulls objects toward the Earth, which is why things fall when dropped. A force can also be something more abstract, like the electromagnetic force, which governs the interactions between electric charges and magnets. These fundamental forces are what govern how matter behaves, from the tiniest particles to the largest galaxies. One of the earliest ideas about forces came from Sir Isaac Newton in the 17th century. Newton observed that when an apple fell from a tree, it was drawn to the earth by a mysterious force. He didn't just notice the apple, though. He also saw that the same force made the moon orbit the earth and the planets orbit the sun. Newton's discovery of universal gravitation showed that gravity isn't just a force that acts on objects on Earth. It extends across the entire universe, pulling everything toward everything else. Imagine you have two magnets. When you bring them close together, they either attract or repel, depending on their poles. Gravity works similarly, but on a much larger scale. Yet, even with Newton's discoveries, not everything made sense. For example, light, which was thought to be simply a wave, didn't fit neatly into Newton's theory. While Newton's laws could explain much of how the universe behaved, they couldn't fully explain phenomena like light's behavior. This led to the development of a new theory that would completely change how scientists saw the world: Einstein's theory of relativity. Albert Einstein's special theory of relativity, published in 1905, revolutionized our understanding of space and time. It proposed that space and time are not separate entities, but are intertwined in a single entity known as space-time. According to Einstein, the faster an object moves, the more its space and time behave differently compared to objects at rest. He also showed that the speed of light in a vacuum is always constant, no matter how fast an observer is moving. This idea of relativity was a huge leap from Newtonian mechanics, where time was seen as something that always passed at the same rate everywhere. Einstein's theory suggested that time could stretch and bend depending on how fast an object was moving. One of the most mind-bending consequences of his theory is the idea that time moves more slowly for objects traveling at speeds close to the speed of light. So, if you were traveling at near light speeds and returned to Earth, you'd find that your friends had aged more than you had, even though, from your perspective, everything seemed normal. But that wasn't the end of the story. Relativity also introduced a new understanding of gravity. Unlike Newton, who thought of gravity as a force between two masses, Einstein suggested that gravity is the result of massive objects warping spacetime. Think of spacetime as a giant rubber sheet. When you place a heavy ball on the sheet, it sinks and distorts the fabric. Smaller objects placed nearby roll toward the ball, as if drawn by gravity. This is how massive objects, like the Earth or the Sun, cause spacetime to curve and pull objects toward them. Einstein's ideas were proven in many ways, but one of the most famous demonstrations came in 1919, when astronomers observed the bending of light from stars around the Sun during a solar eclipse. This confirmed that light, like matter, follows the curvature of spacetime. This was a groundbreaking confirmation of Einstein's theory and a triumph for physics. While Einstein's theory of relativity changed our understanding of space and time, there was still a mystery lurking on the smallest scales. Physicists began to look inward, towards the world of the incredibly tiny particles that make up everything around us. This led to the development of quantum mechanics, another revolutionary theory that explains the behavior of particles at microscopic scales. Quantum mechanics is strange, mysterious, and full of paradoxes. Unlike classical physics, which deals with predictable, deterministic outcomes, quantum mechanics suggests that the behavior of tiny particles, like electrons, can only be predicted in terms of probabilities. This means that, on a quantum level, particles don't have definite positions or velocities until they are observed. It's as if a particle exists in a cloud of probabilities, where it could be in multiple places at once. One of the key figures in the development of quantum mechanics was Niels Bohr, who in the early 20th century proposed that electrons orbit an atom's nucleus in fixed orbits, or shells. But electrons could also jump from one orbit to another, absorbing or emitting energy in the process. This idea helped explain why atoms emitted light in specific wavelengths. Later, physicists like Werner Heisenberg and Erwin Schrödinger developed further aspects of quantum theory, including Heisenberg's uncertainty principle, which states that the more precisely we know a particle's position, the less precisely we can know its momentum. Quantum mechanics has led to extraordinary advancements in technology, from the creation of transistors, which are the building blocks of modern computers, to quantum computing, which promises to revolutionize the way we process information. It also gave birth to lasers, which power everything from barcode scanners to medical equipment. Yet, even today, quantum mechanics and relativity don't fit together perfectly. The search for a theory of everything, one that explains all of the fundamental forces of nature in a unified way, is a problem that physicists continue to grapple with. One of the leading candidates is string theory, which suggests that the fundamental building blocks of nature aren't particles, but tiny vibrating strings. These strings are so small that they are beyond the reach of current experiments. But the theory holds the promise of unifying all forces, including gravity, electromagnetism, and the strong and weak nuclear forces. Physics is a field constantly on the move, with each new discovery opening up new questions. From the ancient Greeks contemplating the nature of matter, to the cutting-edge research into black holes and quantum computers, the journey of understanding how the universe works is far from over. What makes physics so exciting is that it's always pushing the boundaries of our knowledge. Every new discovery brings with it a deeper appreciation for the complexities of the universe, and who knows what mysteries we will uncover next. That's it for today, and I'll see you in the next episode.